Muted? Man. Okay. Fine. So, now I want to answer Celeste's question, although this still isn't doing the green up and down thing, but before it wasn't, and the sound recorded okay. So I'm just gonna rely on it being okay. All right. So Celeste's question was a binary search tree. Can it be a binary search tree if a child meets the qualifications with respect to its parent, but not its ancestor? So for example, if this were 30, it would still be greater than 14, but it would be less, but it would not be less than 27, meaning that this whole tree is not less than this node here. Yes, James?
So my understanding of a binary search tree is that like you always start at the root.
Yes.
That situation is never going to happen because if you get 30, it's automatically going to go to the right of 27.
Ah, yes. So right. So, but the question is, according to this definition, Celeste is very pedantic. According to this definition, if this were 30, it would not violate the definition of a binary search tree. You're right, James, that if you use the method to add to a binary search tree where you're always, choosing left or right based on the root, then you wouldn't end up in this situation. But what if somebody just presented you with this tree and asked you whether it was a legitimate binary search tree? And this 19 was 30 instead. Would the answer be yes, or would the answer be no?
Given that definition, it would be unclear.
Well, given this definition, the answer would be yes, right? Because this definition it only talks about children. It does not talk about descendants. What's that? It's wrong. Yeah. So that was my first instinct too, James. But then I decided I would go to Wikipedia, the ultimate authority. So
the article does mention up top though that searching through a binary search tree is as quick as searching through a sorted array. And given Celeste's example, that wouldn't be true if say the 19 was switched to 30, because then it's not really sorted. So the searching through it wouldn't be as fast as searching through a sorted array.
Okay. Let's okay. Yeah, no, Wikipedia stuff about computer science is not for the faint of heart. Definition. It is a rooted binary tree whose internal node, by the way, what does binary tree mean? Each node has at most 2 children. Whose internal nodes store a key and optionally associated value. Oh no, keys and values. Okay, we'll think about that in a minute. Whose internal nodes each store a key and optionally an associated value, and each have 2 distinguished subtrees, commonly denoted, right, okay. The tree must additionally satisfies the binary search property, which states that the key in each node must be greater than or equal to any key stored in the left subtree. Okay, so who is going to write to this person and tell them they're wrong? Hmm? Well, this one doesn't seem to be accepting comments, but all right. So what's that? Yeah, I don't know. It seemed to have a lot of vocabulary. That's basically why I chose it. This one, however, yeah, this one is, so it should be the value of each left child node must be less than any of its ancestor nodes, right? And this must be more than any of its ancestor nodes. So this one is accepting comments. and I say give them hell. Okay. All right. Okay. So cool. Celeste, was that all of your questions? Oh, I said we'd go back to that key thing.
My last
Damn
question
it.
was about tree being balanced, but we can talk about
About the tree being balanced. Okay. We'll talk about that in a minute. What?
I don't know if you can answer this question, but I have a problem with how they always represent binary trees visually. I was wondering if that's like, is that a convention or? Because to me, I feel like it should be flipped upside down.
Oh.
Actual tree.
Right. No. Yes. Yes. No. Yes. No. You almost never see the tree flipped upside down.
Is there a reason? Like, is there any way I can find out why? Like,
trees grow like this, huh?
Yeah.
Like,
I think it's because we tend to generate trees from the top down.
with the roots go like that.
Yeah, so maybe you can think of it as roots, but but we do call this the root node, and we call these the leaves.
Yeah.
So, but yeah, I think it's this got started on paper, and you start at the top of the paper when you're making a tree. You don't start at the bottom. Yeah.
It's like a blog post.
What? No, this is like a blog post.
Make a blog post about like.
Oh yeah, definitely. Make about why trees are represented top down, but yeah, you almost never see them bottom up.
I just feel like it'd be easier to understand if it was flipped upside down. I don't know.
So sorry. Yeah.
Height and everything.
Yeah, that can be your crusade. That can be your life's work. It can be to try and get trees representations flipped. Okay. All right, balanced I want to talk about later. I will go back and look and see what. Okay, so each internal node stores a key and optionally an associated value. So to me, what that sounds like is that it just stores a small piece of data inside the actual node object, and then it uses a hash out there if it wants to have like a larger piece of data. I don't know though. That and somehow there's like links for everything, but there's no links for that key and associated value. Let's see. They talk about. Logarithm. We can also talk about that. Oh, so much to talk about. Okay. So, cool. Let's start talking about depth first versus breadth first search now that I've answered one of Celeste's 3 questions. All right. What is a breadth first search? If I were to do a breadth first search on this tree, what's the first node I would look at?
7.
2. The first node I would look at would be 2, would be the root. Then I would look at either 7 or 5. I think usually it ends up being 5 first and then 7. Then I would look at 9, 6, and 2. And then I would look at 4, 11, and 5.
Is there a reason you go right to left?
It's because of the data structure you generally use. Like either way is a breadth first search. It's just, I think it usually ends up going the opposite direction. I could be wrong. We'll see. What's a depth first search?
So 2 and then 7 and then 6 and then 11.
Yeah, although it actually doesn't really end up being that way. You'll do 2, and then you'll do 7, and then you'll do 2. Then you'll go back up, then you'll do 6, then you'll do 5, you'll go back up, then you'll do 11, then you'll go all the way back up. So notice that we've looked at this entire subtree before we've looked at any of these here. Depth.
Always go to the left first.
Yeah, and again, I can't remember. It might always go to the right first, in which case we'd look at this entire subtree before we look at any of these.
And it's different if it's like just a regular regular binary tree versus a binary search.
Depth versus no. And as a matter of fact, we're going to look at not just binary trees. We're going to look at trees that can have any number of where nodes can have any number of children.
So whether you do left first or right first would depend more on what you're trying to pull out of the tree. Or
It would
set in the
would
tree.
probably depend more on your implementation than anything else.
But in a real life example, it would matter more on like whether you want the maximum value of a tree.
If it was a binary search tree, yes. Yeah. Wait, whether you do depth or breadth, is that what you asked, or whether you do left or right
like
first?
whether you go from right to left.
Yeah, yeah. I mean, that would, if it was a binary search tree, but often, so let's talk about types of trees that aren't binary search trees. So what's a type of tree that would not be a binary search tree?
Merkle tree.
A what?
Merkle tree.
A Merkle tree? What's a Merkle tree?
It keeps all the data and the leaf nodes, and then all the nodes above that are essentially hashes of the children.
Okay.
So it becomes a really fast way to search through a lot of data.
All right, cool. I'm thinking of something simpler. Yeah, no, that's cool. That's cool. Let's talk about an organizational type tree. So, all right, am I going to do the camera thing on the whiteboard? I think I am. All right, so give me a sec. Let me, oh, but I did this without visuals, and that's it.
About just like any representation of data.
Yeah. So,
Family tree.
yeah. Although family trees are a little weird because like you have these two, like instead of things being a children of just one node, we don't have asexual reproduction. We have sexual reproduction. So like each child has two parents, which actually violates the math or the computer science definition of a tree. Yeah, each child can have only one parent in order for it to be a tree. If you have more than one parent, it's a graph. Talk about that next week.
So I mean, HTML in that sense is a tree. Like if you have a series of like divs and stands, like you can only ever have.
Oh, HTML,
like
yeah.
HTML can only have
Yes,
like one
absolutely.
direct parent.
Exactly. Yes, HTML. For sure. The DOM is a tree.
Like organizational diagrams.
Yeah, an org chart, which is sort of what I'm going to do here. So let's go. What is what's that chart thing that I've recommended? Thank you. So I just want to make a chart. No, wait. Okay. I'm obviously logged in.
Document.
I think it's a Google extension.
Wait, where was documents?
Oh, it was at the top where you were signing.
Ah, God. You missed a lot of me like floundering around there, Celeste. Okay, so let's make a new document. It'll probably yell at me that I need to get an enterprise. No, all right, cool. So just for now, so here we have this, and we'll say that this, we'll call Carla the top of our org chart. Fine. No, you won't. Really? You're going to make me do this? Okay. And then beneath Carla will be the squad leaders. So we'll put here and, oh, apparently you can't duplicate that way. Oh, okay. Okay, and Puneet and Dev and Di. Okay. And then under Bonnie, we'll put, I'm just going to, please don't take this personally. I'm just going to do a few people because that's all I've got right now. James and Toya. Okay, and Puneet, who's on in Puneet's squad?
Me.
Patrick. And did I hear Jack making Puneet-like noises? Oh, Jenny. Okay. All right. Let's see. Who's in Dev Squad? Celeste. Okay, and who else? Okay, and Die Squad. There you go. Well, then you get represented. Okay. All right. So, fine. And I'm not going to put in the lines, but you guys can put the lines in yourself. All right. So let's make this tree. Okay. All right. So if I'm going to make it here, and I'm going to call this LG tree. Okay. So, cool. So how do I make a tree?
You declare a constructor, so it'd be like function uppercase tree. That takes a value.
What's it going to take?
Node.
Yeah. So if we have a tree class, basically the tree class basically just needs a node. You might, if it was the Learner's Guild tree, you might put other things in the tree class, like you might put the location of the Learner's Guild and, you know, a description of the Learner's Guild or something like that. But in general, if you're just, and the fact is, if the tree is just a node, the question is, how much value is this, right? How much value is it to refer to the tree rather than just referring to the node? Does that question make sense? No. So if I told you that this was the Learner's Guild tree, I would not actually give you all of these nodes. Just like if I were to give you a linked list, I would not give you all of the nodes in the linked list. I would just give you the head node, maybe the tail node as well, maybe the length. For a tree, it really only makes sense to give you the root node. You don't keep track of all the leaves. That would be insanity. So basically, a tree just has a head, if we're thinking of it in linked list terms.
So are you saying you only give the constructor the head node, and then like when you're creating an instance of it, that's when you're giving it all the data?
No, what I'm saying is that the tree itself, if I want to tell you what tree I'm talking about, the only thing I have to give you is the head node. Everything else follows from there. It's just like if I want to tell you what linked list I'm talking about, the only thing I have to give you is the head node. This data is stored as part of this node, and actually only these are stored as part of this node. These are stored as part of this node, and these are stored as part of this node. The tree itself does not contain this entire information, even though when you think about it, that's what it is. But in order to designate this tree, I do not need to give you all of this information. All I need to do is give you this. Each child node is a tree too. This is the Bonnie tree that has the root Bonnie. If I want to talk about this tree, I just give you Bonnie. If I want to talk about this tree, I just give you Kelsey.
So even if like the leaf doesn't have any children,
It's still a tree. It is a sad, childless tree.
So each individual leaf is a tree. That's it.
Every node is a tree. So each of these is a tree. Each of these is a tree. This is a tree. They're all trees. Every node is a tree. Or I can say every node is a tree that's determined when that node is the root. So I can say the tree, Bonnie is representative of the tree that has Bonnie as the root. Jack is representative of the tree that has Jack as the root. The tree Bonnie has 3 nodes. Tree Jack, 1 node. The tree Carla has 1 plus 4, that's 5, plus 8 is 13 nodes. The tree Carla has 13 nodes. Is this feeling okay? Okay.
Tree Carla, because the only nodes it knows itself are its 4 nodes.
If I'm telling you that the tree is Carla, if we were using this definition of a tree, the only node that the tree would know about would be Carla.
But then it also knows.
But then when you access Carla, Carla knows its children. Then when you access each of the children, they know their children. Yeah. It is a lot like a linked list in that you don't get everything at once the way you do with an array. You have to traverse it. Okay. So often you don't even have a tree class, since each node represents a tree with itself as a root. So I'm just going to make a tree node class. Oh, we were doing, man, I'm, okay. For a binary tree, it would look like this. What form would children take?
An array, maybe.
Ah, an array. Why would an object be better, Jack?
Access them immediately. Let's say which child. Oh, actually, that would not be better.
Yeah. So basically, I could use a set if I didn't care about order. But I want James to be on the left and LaToya to be on the right. And as a matter of fact, since we said this, well, okay, so for this, I mean, obviously this is the order of superiority among the squad leaders. So I do care about order here. So okay. I do not know JavaScript as deeply as I know Python. So I do not know that this is necessary, but I'm assuming it is.
You could just, like, in the function itself, where you're passing the arguments, you could do, like, children equals, yeah.
You cannot do this in Python, and I'm assuming that you can't do it in JavaScript either. It's subtle. This array is going to get declared, or is going to get created. This empty array is going to get created when you declare the function. Not when the function runs, but when the function is declared. And that means anything, and since arrays are mutable, that means any node that I try and instantiate without any children is going to share the same array. We haven't talked about memory a lot here. Try it. Try it. And if we have time, which I don't think we will, I'll try it here. In Python, if you made a bunch of nodes and then you started adding children to the nodes, any node that started out without children will get any children that you add. Like this is bad news in Python, and I'm guessing it is in JavaScript as well. Okay, so okay, actually we want to make Carla last because then we can hand Carla children, right?
Need the new keyword.
Thank you. Patrick, Jack, Celeste, Kelsey. Jonathan, Alex. Okay, so, and my children are going to be James and Latoya, like that. And then for Puneet's children are going to be Patrick, Jack. Dev's children, Celeste. Can tell your kids they got a new brother and sister. Babysitters. And this was Jonathan. Okay, and Carla's children are, okay, cool. So now if so now I've got a tree, and my tree is called Carla. And I want to do a depth first search. So I'm going to say tree node.prototype .depth first search. Okay. And so now, and I don't need to get anything because the node that I'm talking about will be represented by this. All right, so what do I want to do? So basically, I want data, or to find, let's say. So I'm doing a search, so I actually want to find something. There's something I want to find. Okay, so what's the first thing I'm going to do? So if I'm here, and I want to see if Celeste is at the guild. So my to find is going to be Celeste. How am I, what's my plan? I have to start here because I'm starting with the tree called Carla. And I want to do a depth first search to determine whether Celeste is at the guild.
You go to Bonnie.
You go to Bonnie, go to the first child.
Yeah, and then you go to your kids. Look, is Celeste there? No, it's Celeste. go back to binary. No. Then go to top and then go to punit again. So each of them until you find.
Okay. Okay. So that's generally what I want to do. There's a couple things that you left out. One is that I need to make sure that Carla's not Celeste. If Carla was Celeste, boom, I'm done. So the first thing I'm going to do is if to find is equal to this dot data, return true. I found her. Otherwise, I need to start looking at the children. I want to keep track of who I want to visit next. Yeah. So this now, I actually don't want just, well, so I can do to find, but I also want to keep track of to visit. And I'm going to keep track of to visit in an array. I'm just going to keep a running tally of people that I haven't checked yet. All right. So again, I'm going to say let's say to visit equals to visit or an empty array, right? If I call this without to visit, then I'm just going to say there's nobody for me to visit. Okay. Then if to find is this dot data, then I'm going to return true. Now, otherwise, what am I going to do? What do you think, Celeste?
What version we call it on this dot whatever's in the array?
So you want me to do, well, so I have to do something dot depth first search. What's my something going to be?
Children?
This is a problem. Why is this a problem?
Doesn't know who the children are defined.
No, this dot children is totally defined. This is just whatever node it is. This is completely defined.
Well, it's not because it's an arrow function. but we can get
No. I actually, oh, darn it. Okay, yeah. Okay, you happy? Okay. Why is this a problem?
There's no depth first search method on an array.
We don't have a depth first search method on an array. This dot children is an array. You can't just run it on an array. Back to XXX.
It's not children, not for each.
Okay. All right. So if I do a this dot children dot for each, and I want to make sure that I'm returning.
That's going to return undefined, though. Because for each returns undefined. It doesn't return an array or anything.
Well, so how am I going to get that?
Like a map.
Okay.
So they go forward.
Why did I bother doing this?
First you can populate it and then pop or shift off.
Yeah. Okay. So let's so I'm going to say now, I'm going to add things that I want to visit, right? I know how to do this in Python. I don't know how to do it. How can you add a whole array? I guess you could say plus equals. Can I do that?
You could do a concat.
Will this work? Probably not. It'll probably just like add an array as the last item. So I do like this.
You could just like toVisit.concat
Hmm.
and then pass concat the array that you want to add to it, basically.
Got it. Now the question is, once I've concated that, what is my next node going to be? So I've added that I want to visit some stuff. What is next node? Like, how am I going to determine what I want to actually visit next? That later.
You need
Check
to
it.
somehow, yeah.
Yeah. Okay. So let's talk about this. If we're going back here, so my toVisit, I'm just adding all these children, right? Let's say that I choose Bonnie. Let's say that I choose the leftmost one, right? Then, fine. So I choose Bonnie. And now my toVisit, let me, so my toVisit now looks like Bonnie, Puneet, Dev, Di. Okay, so let's say I choose Bonnie. I take the leftmost thing in my toVisit, the first thing in my toVisit. If I choose Bonnie, then I'm going to go and I'm going to look and see, is Bonnie Celeste? Not last time I checked. So then I'm going to add to my toVisit, I'm going to add James and LaToya. If I'm doing a depth first search, do I want to look at Puneet next? No. Are you guys following? So really, for a depth first search, I want to look at the end of my toVisit list. I want to start with Di, and this is why I was talking about how some of them start on the left. I want to start with Di. Then I want to add Jonathan. Di is not Celeste, okay. Then I want to add Jonathan and Alex. So basically I end up removing Di. So when I do this, I want to otherwise I'm going to keep visiting that, that one over and over. So I'm going to end up removing Di. So this is how it's going to look. This is why it's easier on a whiteboard. Okay. So I'm going to end up removing Di, determining that Di is not Celeste, then adding the children, Jonathan and Alex. And then for my next trick, I'm going to look at Alex. So it's important that we look at the end of the list if we want to do a depth first search.
I would have automatically assumed when you said depth, the end of the list going down, not that one.
I'm sorry, elaborate.
Before you explain this,
Yeah.
you had said depth first.
Yeah.
I would have thought the furthest down because it's deepest down.
Yeah, well, yeah, oh, I see. Yeah. This is an array, and so, you know, it could be sideways or, you know, however you wanted it to be. Okay, so how do we get the last thing from the array? Yeah, but we want to remove it as well. And believe it or not, that's it. That's our depth first search. Recursion, ladies and gentlemen. Oh, not quite. Sorry. What if we didn't find the person? How do we know when to stop recursing? Not when there's nothing to pop. It's actually when we hit a leaf. Right? We're going to recurse. In this case, we're going this way until we hit a leaf. And we do not want to run this on Alex's children because Alex has no children. That we want to start going back up. So if
to visit.
if we've hit a leaf and we've got nobody else to visit, what's our situation? What's that?
It's not in the tree.
It's not in the tree. That's basically going to happen when we hit James over here. We've hit a leaf and there is nobody else to visit. That means that we have never returned true. So at this point, we're actually going to return false. Otherwise, what do we want to do?
You want to like go back one and then run the recursiveness again.
Yeah. How do we do that?
Aren't we already? But like, so if we go back to like the tree, like the diagram, we push all the children in. So we push in like Bonnie, Puneet, Devin, Di.
Right.
And then Di has children, so we push in Jonathan and Alex. We go to Alex, and there's nothing, but we removed Di, so we wouldn't get to Jonathan.
We would though, because we pushed Jonathan.
Oh yeah. Okay, so I was right in the sense that then we could just return to our to visit and then run this again on Jonathan, and then yeah.
Right? If there are children, just throw them on. If there aren't children, determine whether we've run out of people to look at. In that case, return false. Otherwise, we're not changing the to visit. So when we get to Alex, we only got to her because we removed her from the end, because that's the way we get to that's the way we recurse, is we pop it off of our to visit. So we got to Alex. Alex has no children. To visit, what is our to visit length 0 at this point? No, our to visit looks like this. So we're not going to return false. We're not going to enter this else because she had no children. So we're just going to pop off the next node. We're just going to look at Jonathan next. Then we pop off Jonathan. Jonathan has no children. Oh, Jonathan is not Celeste, right? Jonathan has no children. To visit is not empty. So we are not going to return false. We're skipping this because we entered the no children condition. So now the next node that we're going to visit is what? Dev. You guys with me? So we pop Dev off. Now we're at Dev. Is Dev Celeste? No, he is not. Does Dev have children? He does. So we're going to add his children. Ooh, things are getting exciting. Celeste is showing up on our to visit. Then we're going to determine our next node. Our next node is Kelsey. Is Kelsey Celeste? No, he is not. Let's see, does Kelsey have children? No, but we still have stuff in to visit, so we're not going to return false. Now next node has become Celeste. So now to find actually does equal this dot data. We're going to return true. And then we're going to have to, right now our stack is several levels deep because we've recursed a few times. So we'll pass that true up the whole stack. And if you want to see this in action, you can use that JavaScript tutor until we return true. Let's run this and do some printing. Okay. So let's see. And then here we'll say okay, and then here we'll say if I make everything caps, it just dilutes the effectiveness. Okay. And then and let's just put a new line before the about to visit. Just so about to visit. Okay. All right. Should we do it? God damn it. Okay. Cannot read data of undefined. Okay. All right, so it added the kids. Okay, so let's figure out what we did wrong. When I say we, I completely blame all of you. Let's see. Did you figure it out, Celeste?
Scroll up a bit. No.
Let's just see what it thinks next node is. Although, I mean, it should be this fucking tree node. All right. Okay, next node, undefined. Can you not pop? Am I just like? Is it because I don't understand what concat is? Do I have to say to visit equals to visit dot concat? Yeah, I was led astray.
We're all blown away. What?
Maybe concat returns a new array.
Yeah, that's that. Yeah.
Yeah.
Well, yeah. Okay. So first thing we do is we add Bonnie, or I should also say about to visit. Actually, let's do. Okay, so examining Carla, we added all of Carla's kids, and then we're about to visit Di. Examining Di, we add Di's kids. Now we're about to visit Alex. Examining Alex, we don't add anybody because Alex has no kids, and we're about to visit Jonathan. Examining Jonathan, Jonathan has no kids, about to visit Dev. We add Dev's kids, and then we pop Kelsey. Kelsey has no kids, and then we finally find Celeste. Let's let's make sure that this returned true. Okay, so it returned true. That's good. And now let's search for somebody who's no longer at the guild. I know, that's too sad. Let's search for Jen, who's not here today. Okay. Did not find.
Oh, it's had fun.
I know. I know we're over time, so I just want to wrap up with a couple things. First of all, what data structure did this remind you of when I was using this to visit here? A stack. Last in, first out. If I want to do breadth first search, you guys, that changes it to a breadth first search. Making it a queue instead of a stack changes it to a breadth first search.
It would also it would increase the time complexity.
Because if I'm using an array as my to visit, for sure.
I'm sorry, what's putting 0 in there do?
Instead of popping at the end, I pop from the beginning.
Yes.
Same as shift.
This is how you would do it if it was Python. If you were like my sister, your brother Python. Crazy. If you use a queue instead of a stack, it's breadth first. Because then I run through all of these, right? As Bonnie, Puneet, Dev, Di, and if I pop Bonnie, and I'm still adding James and LaToya at the end, but then I visit Puneet and add Patrick and Jack at the end. Then I visit Dev and add Celeste and Kelsey at the end. You're visiting all of these children before you visit any of these. Oh my God, trees are fun, right? sit with it for a while. I will make this code available to you so that you can play with it. Patrick, you can do your thing to see whether this gives you trouble or not.
Yeah, I think, like you pointed out, when you have to like keep creating multiple arrays, you probably would have issues. I know it works when you only have to create like one object or array.
Yes. Well, okay. And right. And then, you know, you can do more of this, like looking at it in JavaScript Tutor. You can console log out stuff to examine it. This is really good stuff to play around with. All right, cool. Thanks for staying over.
Thanks, Bonnie.